Well, hello, grade 12s. Welcome to another amazing edition of Mr. Flynn's videos. Yeah, I'm sure you've heard that looks like the schools are going to be closed for some time. They're not even announcing a date. I would say probably at least May. So let's make the most of it. It's so gratifying to see you being successful using these online tools. Like for example, Hala finally figured out where the homework was. Not that it wasn't totally obvious or anything, and everyone stopped whining, which is good. Okay, so with that out of the way, I just wanted to show you how to do a question like this. So this is going to be a short video. It's again on the concept of impulse and momentum. So look, what do you do if the force is not constant? And there's a question in the textbook like this, so I just wanted to show you this example. So in this example, there's a force that's variable. Okay, it first increases, then decreases, acting on an object, and that's really more realistic. This, in real life, that's what happens. Let's say you hit a ball with a bat or something. It's not a uniform force usually. It's usually non-uniform, and at first it starts out small, gets bigger, and then peaks, and then gets smaller again. But anyway, how do you figure out the impulse on something like this? Well, I'm just going to remind you what impulse is. Impulse, my wonderful writing on the screen here, is equal to force times time, right? But what happens if the force isn't uniform? Well, what happens is it's also equal to the area under the force time graph. And we've done area before when we looked at the area underneath a velocity time graph is equal to the displacement. So this is kind of something similar. Okay, so impulse is the area underneath the graph. So this area in here, I'll just color it in like that for you. That area, okay, I'll use a different color. This area here is the impulse, okay? So we've got numbers here so we can actually work out the impulse. So let's say in this example, okay, so in this example question, let's say the mass in this problem is equal to, keyboard. Okay, so let's say the mass is equal to, I don't know, 1.5 kilograms. Okay, and we have this graph where this force is acting on this 1.5 kilogram mass. So I'll ask a couple of questions. Number one, what's the impulse? So question A, what's the impulse in this graph? So it's pretty straightforward. Impulse equals area. And the area here is just half the base times the height because it's a triangle. So that's equal to half of 40 is 20. 20 times, we'll say that is approximately 100 up there. So 20 times 100 is 2,000. So the area is equal to 2,000. And the units are same, like newtons times seconds. That is a typical unit of impulse. Force times time, right? So the area underneath the graph is equal to the impulse. And we found that the impulse here is 2,000 newton seconds. So that's question A. Now, question B. How fast would the object be moving if it started from rest? So if V1 equals 0, then I'll use the prime notation. What is V prime equal to? Okay, so what's its final velocity? That's kind of an interesting question. We've never really done one like this before. So you have a variable force acting on an object. How do you find its final velocity? Well, you just have to use the other definition of impulse. We know that impulse is also equal to the change of momentum. So it's mv prime minus mv. We looked at that in the last lesson. Okay, so all you have to do is substitute 2,000 for the impulse, which is the area underneath the graph. The mass is 1.5, that's why we needed it. So it's 1.5 times v prime minus 1.5 times 0 is the initial velocity. So now all we have to do is divide 2,000 by 1.5. Okay, so 2,000 divided by 1.5 is v prime will equal 1333.3 meters per second in the positive direction, right? So it's a positive force, so it's in the positive direction. And there you go. So that's a very large final velocity, but I mean, this force was applied for 40 seconds, and it went up to 100 newtons, and it's only a 1.5 kilogram mass. So it's a very large force on a relatively small object. So you get a big velocity, okay? All right, so that's it. That's it for this. I just wanted to explain how you do a question like that. And I know there was a question like that in the homework. All right, so that's it for now.